Alright, good evening everyone. Thanks for coming to our talk this Tuesday evening. Before Sean starts, I would just like to mention a few things. So tonight's talk is sponsored by the SEI, and the SEI stands for the Society of Chemical Industry. They offer student memberships and a lot of networking and careers opportunities. So it's definitely something to think about if you're, thinking to carry on in chemistry or very interested in the chemical industry right now. Also, they have an upcoming event called the Bright SC Idea Challenge. This is a competition amongst uni students promoting innovation and new technology, which offers access to exclusive training material. So the webinar for that will be tomorrow. If anyone's interested, please check their website and yeah, you'll get to know more there. So about Sean Sargent is the Chief Executive of the Green Lithium company, trained as a maritime civil engineer and is a fellow of the Institution of Civil Engineers. He has worked in process and infrastructure programs, predominantly in the nuclear industry for the last 30 years. During this time, he was the site director at Berkeley Nuclear Power Station and program director for a program to retrieve, process, and store intermediate level radioactive waste as part of Madnoc's decommissioning program. Sean has worked for Jacobs Engineering during much of his career, where at different times he led the nuclear new build business, the defense business, and post-acquisition integration teams. He moved to Green Lithium to get involved with the energy transition. Okay, so I'll give up to you now, and thank you.
Thank you very much, Jenny, and it's a pleasure to see you all. Thank you all for coming. I've got to say, this is the first time I've ever given a lecture with such an intimidating periodic table staring down at me with lithium almost in the top left-hand corner. So, that just reminds me why we're all here. So what I'm going to talk about today, and I was very keen that Jenny emphasised my civil engineering credentials. I'm not a chemist, I'm not a physicist, so if you ask any difficult questions, I reserve the right to not answer them. But I'll tell you what I do know, and hopefully if you've got any questions at the end, I'll talk to you about it. The whole point about the talk today is really to talk about how we enable the electric revolution. So what do we mean by the electric revolution? Fundamentally, the whole world needs to change. If we're going to achieve our 2050 global climate change objectives, we just need to stop burning fossil fuels. And we all know it's going to be a transition. It's not going to be something that happens overnight. But what Green Lithium is about is making sure we do that in a low carbon sustainable way. It would be very easy to electrify everything, but actually burn just as much carbon dioxide, produce just as much carbon dioxide, and do things just as unsustainably as we were before. So we have to change the way we do things, and it can be done. And just to illustrate what I mean, so everybody understands that electrification of transport predominantly means electric vehicles. It means batteries to drive electric vehicles. It also means a lot of other things, hydrogen propulsion and so on. But there's an example of a nickel refining technology that's just been developed. So it takes very low-grade nickel ores. It's a very energy-intensive process. It uses a pyrometallurgy process. It heats up the rock a lot to get the right type of nickel you need for subsequent refining. If you buy a car with some of that nickel in it, you've already got a carbon footprint that's higher than an internal combustion engine vehicle over its whole life. So you think you're buying an electric vehicle to do the right thing for the planet. Actually, you've just taken a step backwards. So it's really important that we concentrate on decarbonising and making sure we've got sustainable processes as we move forward. And something that you'll see again and again, people say, hard rock lithium refining, that's a dirty process, it's energy intensive. Well, it doesn't have to be. What we're proving at Green Lithium is there's another way to go about it, and there's a way to solve some of those problems. It's not necessarily the cheapest way to do things, it's not necessarily the easiest way to do things, but there is a route map you can follow to decarbonize your industry, and that's what I'll talk about today. So first of all, I'll tell you a little bit about the way things work. So how do you get lithium into an electric vehicle? So the first thing is there's two types of lithium that are currently refined for electric vehicle batteries. About 50% come from brines, predominantly from South America. They use enormous salars, so evaporation ponds where the sun's radiation drives off the water and then slowly various salts precipitate out until you get left with lithium chloride, which then can be refined into battery-grade chemicals. The way they do it is they pump a lot of groundwater out the ground. So it has quite a big environmental impact, and they face quite a lot of criticism over the years for doing that. So there's a more modern version of that, direct lithium extraction, where you can pump water from deep underground, geothermal water, and use a process of effectively an ion exchange process to refine the lithium. About the other 50% of lithium that goes into electric vehicle batteries comes from hard rock. So we mine lithium-bearing ores. In our case, it's a spodumene. So the mineral is called spodumene. It's a lithium-bearing mineral that can be concentrated. So we take the spodumene concentrate. That comes from mines initially in Western Australia. But as the market picks up and there's more and more realization that there's this huge market potential, we're seeing more mines opening in places like Canada and South America, in sub-Saharan Africa, so places like Namibia, Ghana, Mali, Zimbabwe, Mozambique, I could go on, Ethiopia, but also in Europe. So there's a mine that's just been opened up in Finland. There's another one that's going through the permitting process in Portugal, and another one in Spain. So you see there's reserves closer to home. And there's other minerals. It's not just about spodumene concentrate. There's other lithium-bearing minerals. So those lithium-bearing minerals get pulled out the ground. They go through a beneficiation process to improve the concentration of the lithium. They then get shipped to a refinery somewhere. That's our part. So we're building the refinery. And then you've got this whole complicated supply chain of the lithium goes into the cathode end of the cell. And that's along with all the other parts, the nickel, the manganese, the cobalt. Somebody else makes the anode, often out of graphite, and then the two get put together. They get assembled into modules, and then the modules go into cars. Now, at the moment, those middle two steps are almost completely done in China, which works very well for the predominant type of battery technology that's used at the moment. So most batteries are what they call LFP batteries, and they use a lithium carbonate in them. And lithium carbonate travels very well. It's it's got a good shelf life. It doesn't degrade over time, and that works really well. But in Europe, there's a bit of a change coming. They want to move away from cobalt-rich batteries. There's all sorts of problems with artisanal mining of cobalt. They also want to go for higher power density, higher range batteries, faster cars, you can imagine. So they tend to go for higher nickel content cells. And the lithium that's used in those batteries is lithium hydroxide rather than lithium carbonate. The problem with lithium hydroxide, it doesn't ship long distances well. It very readily absorbs CO2 from the air. It can absorb moisture, and it tends to cake. So after a very small number of months, it sort of becomes, the purity drops, and it becomes unsuitable for battery technologies. So what that means is you've got to bring the supply chain to where the batteries are being made. And you all have heard about the gigafactories being built in Europe, particularly in Germany and Poland. There's some being planned in Scandinavia, but also in the UK. So we've got AESC Envision based up in Sunderland. We've got British Volt planning another facility in Blythe, again in the northeast. We know that Jaguar Land Rover are planning a gigafactory. There's other companies. Innovata are planning a UK gigafactory as well. So our plan is to make the lithium hydroxide in Europe's case. We'll be selling that to the cathode producers. The cathode producers will be working with the gigafactories and producing the cells. And our plan is to be as close as possible to one of those clusters where batteries are going to need these raw materials. And then that whole assembled cell goes into an electric vehicle. Now, to give you an idea of the scale of this challenge, currently almost no lithium hydroxide is refined in Europe. It's all very close to zero. There's one refinery in Russia, which suddenly isn't doing as much business as it was a few months ago. But apart from that, there's barely any production at all in Europe. And yet the demand over the next 5 years is going to go up to between 600 and 800,000 tons per annum of lithium hydroxide monohydrate. So somebody's got to refine all that material. Now, by anybody's standards, what we're planning is a big refinery. It makes about 50,000 tons of battery-grade lithium hydroxide per annum. That's only 6% of that European market. So even if you had another, I don't know what the math is, but 18-ish people did the same thing as us, would only just be meeting that 2030 demand. So that makes you realise there's actually a mountain to climb here. We need as many people as possible, and that's just the lithium. The same thing has happened with the nickel, the manganese, with the anode production, with the cathode production. This is a whole new industry that's going to be born and will have to grow over the next 5 to 10 years if we're going to meet that, that demand. If we don't meet that demand, then the electrification of transport will falter. We'll actually not achieve what we need to achieve to reach the 2050 climate change goals. So personally, for me, this is a proper mission. You know, we've got to do everything we possibly can. So has everybody else. Otherwise, this transition is going to falter. So I've put this in for you. I can't pretend to be a hydrometallurgist or a pyrometallurgist, but it's just to give you a snapshot of the process we're talking about here. So you've got 3 parts to it, really. You've got calcination, which is basically baking the rock. You've got the center section, which is the hydrometallurgy. That's the clever bit. And then at the end, you've got crystallization, where you produce the lithium hydroxide monohydrate. So I'm going to go through those in civil engineer level of thinking. So you've got calcination, hydrometallurgy, and crystallization. And just to give you a bit of context behind the decarbonisation plans, we'll talk a little bit about what happens in these processes so you get a sense of the challenge. So first, calcination. This is taken from a render of our design. So these rotary kiln ovens look very shiny and new. Trust me, they'll look nothing like that after about a week of operation in the northeast climate. They'll be nice and rusty and making a right old racket, I should think, as well. But fundamentally, so these are gas-fired rotary kiln ovens. They're huge. They take about 28 tons per hour each. So we've got 2 lines to produce that 50,000 tons per annum. So the materials continuously fed through them. It's a 24/7 operation, almost 365 days a year, but you know, various time for maintenance and outages and so on. And in these ovens, the top cylinder of the 2, the material's heated with gas burners to get to about 1050 degrees C. And then the second tube is where the material's cooled. So in the first tube, it's about 2 hours. Getting heated up to that temperature to change the spodumene nature, and then the second one is cooling it down, ready for the hydrometallurgy process. So you know, in that process, you burn a lot of gas. So that's challenge number 1. How do you reduce the amount of gas you burn? And what that process is designed to do, so the spodumene you dig out of the ground is alpha spodumene, so it's not water soluble. Therefore, you can't use a hydrometallurgy process to convert it. But putting it through the calcination process, it converts it to beta spodumene, which is water soluble. It's a decrepitation process that happens to the spodumene. The second part of the process, the difficult bit, the hydrometallurgy. So this is a series of autoclaves and reactor vessels, which are basically the cooking pot. You control the temperature, you can control the pressure, but you go through various stages until you convert the material to what you want it to be. We've got a 2-stage process. It was originally called the Quebec Method for converting spodumene to lithium salts. And the Metso Outotech, so our technology partner, they're based in Finland. They've been working in mineral processing for about a century. They've been working with lithium for several decades. They took the Quebec Method and have been doing a lot of R&D since about 2000. And in 2017, they patented a new flow sheet that took what they call the alkali leach process and refined it. So making the footprint much smaller than the traditional way by using autoclaves, so a bit like a pressure cooker, and that reduces the energy requirements as well. So basically the beta spodumene comes out of the calcination, it's cooled down. The next step is to grind it up so that you can turn it into a slurry and start pumping it through the hydrometallurgy process. The first stage is a pressure leach. It's in an autoclave, a big pressure vessel, huge pressure vessel, where it's heated up to about 220 degrees, 28 bar of pressure, and it spends about 1.5 hours being circulated and recirculated. That's with soda ash. So what you're after here is a conversion to lithium carbonate through the sodium carbonate. The second stage is an atmospheric leach, so it's much more the reactor vessels that were shown in the photograph. It's not an autoclave now, it's just done with atmospheric pressure. But the reagent here is lime. It's in fact quicklime, so you add quicklime to the process. That's calcium hydroxide, that gives you the conversion to lithium hydroxide. I'm simplifying it hugely. There's all sorts of recirculation loops to really optimize and get the efficiencies that are required for the process. And there's a lot of clever people working that stuff out. The main feature of the process, so every other refinery in the world today uses an acid leach process. It uses sulfuric acid. It's a much higher temperature, higher pressure process. And you can imagine using sodium sulfuric acid, it's not selective at all. Everything gets dissolved. But using an alkali leach process, it's very selective. Controlling the alkalinity means that you can get the lithium out much more selectively and leave everything else behind in the byproduct. And I'll talk about the byproduct more in a minute, because that's a really important part of how we make the process sustainable. And then finally, you've got the crystallization stage. There's a nice shiny example up there. Ours is actually a two-stage crystallization. This is how you take the lithium hydroxide. You remove some of the last metals. There's some silicon and some potassium that come out through the crystallization process. But this is where you use evaporators and various processes to reduce the moisture content until you get to the monohydrate crystal of lithium hydroxide. And I think there's just a tiny bit of detail. So you go through various ion exchange processes, filtration processes, removing the byproducts, and then finally that two-stage evaporation process to get to that final salt. I said I'd come back to the byproduct. So for that 50,000 tons of battery-grade lithium hydroxide we produce about 600,000 tons of byproduct. Now, I don't know if any of you can imagine how big a pile 600,000 tons of anything is, but you know that's a big pile. And if we don't find a home for that material, we've got a bit of a problem. And you can't really claim to have a sustainable process if you're producing 600,000 tons of a byproduct that nobody wants. Okay, so what is it? It's an analcime sand. So this is an aluminium sodium silicate. That's about 70%, about another 15 to 17% is calcium carbonate. And then there's other minor minerals. So anything that you don't want ending up in the lithium hydroxide pretty much ends up in this byproduct. So anything else that was in the original raw materials will end up in this. You can see it comes out from the filtration process as a filter cake. It is slightly pozzolanic. That's the first clue as to the potential downstream markets. So pozzolanic means it's a bit like cement. So it will actually cure it, hydrate, and actually can make almost like a cementitious binder type material. It comes out quite wet. That's a problem because most applications, most markets like dry material. So that's something we're going to have to work on. We're going to have to look at how we dry that material. It's quite alkaline. So you've still got that pH of 10 to 12. Again, we might have to control that. So there might need to be some post-processing of the material to get it to something we can use. But the thing about the analcime, and I'm really sad to say I can't say too much about it at the moment because it's quite commercially sensitive, is when you start looking at it, you start doing some research into the material and its potential applications, you realize that it's not just sand, and actually it's a very, very interesting material. And the applications we're looking at are all around helping the construction industry reduce its carbon footprint. So an eighth of all carbon dioxide that gets pumped into the atmosphere today comes from cement production. And this is a material that could significantly replace the amount of cement that goes into concrete. So there's a lot of work to do. There's a lot of R&D to support that and work out what we need to do to this material to make it suitable. But if that works, you can see instead of having a 600,000 ton problem, which is a big problem, just to reiterate, it suddenly becomes a 600,000 ton opportunity. So it's really important that you focus at the beginning on these circular economies. You don't think of these as waste products, you think of them as byproducts. You think, what else can I do to them? What extra conditioning do I need to do to make that material reusable in a downstream market? So, decarbonisation. So this is my 7-step plan to decarbonisation, okay? Oops, got a bit ahead of myself there. So the first thing, and we talked about this already, but the first thing you do is you select as low a carbon technology as you can. So that's one of the reasons we selected the Metso Outotec process. We know its carbon footprint is lower because of the lower energy demand, because of the lower pressure and temperature. But you can't just take the vendor's word for it, you have to check. So what you do is you get an independent carbon life cycle assessment. There's an international code for how to conduct an LCA. And what that does is it takes a typical refinery, in our case that would be an acid leach process as per all the existing hard rock refineries in the world today. They've looked at their carbon footprint and then measure us against that. So if you said an acid leach process might have a carbon footprint of 16 kilograms of carbon dioxide per kilogram of lithium hydroxide monohydrate, we've got to get that 16 down to 0 before I'm old and dead. So that's the challenge. That's the goal we've set ourselves in Green Lithium. And by selecting the technology, we get an instant dividend. We get that down to 12 kilograms. So we instantly get a 25% reduction in carbon footprint. That's by doing nothing clever at all, just selecting a more modern progressive technology. Then you start whittling away at it. You work out what else you can do. So for example, electrification. What if we didn't heat the spodumene entirely with gas? What if we preheated it with electrical heaters? Then you can reduce that gas burn in the calcination phase. What if you don't burn gas at all? What if you burn hydrogen? Well, that's really significant. Instead of burning natural gas, which produces a lot of carbon dioxide, if you burn hydrogen, you've eliminated a huge amount of carbon dioxide. There's still some that comes off. If you bake rock, if there's any carbonate, you'll tend to drive off carbon dioxide. But you really do get a real chunk of reduction by swapping to hydrogen. Of course, it's not that simple, because blue hydrogen's got a different footprint to green hydrogen, which has got a different footprint to pink hydrogen. You've got to understand all those, and you've got to put countermeasures in place to make sure you're getting the most bangs for your buck in terms of carbon reduction. You can use things like energy recycling, heat capture, to make sure that none of that energy is wasted. It's not just going up a chimney somewhere that you're capturing it and reusing it. And as I say, that hydrogen roadmap is just probably the most important thing. You don't get hydrogen without selecting your site well. So you need to choose a site that gives you access to renewable electricity. That's really important. If you electrify a process, you've got to make sure it's renewable energy. So it's got to be close to either solar power or wind power or both. Or if you can't do that, then you concentrate on other low carbon power sources. So biomass is probably the next best thing, and nuclear is also very low carbon. But that comes with site selection. You've got to put yourself in a proximity where if you're going to get a private power supply, you're not running the power supply too long. But in fact, what you do is you connect up to grid, but you sign a special agreement with a low carbon energy producer. The carbon capture is really important. It's got to be somewhere which gives you carbon capture, because at some point you're going to have to capture your carbon dioxide. It might just be the residual carbon dioxide. It might not be the big kind of government-sponsored plants that you see. It might be small modular carbon capture plants. But whatever we produce, however we get it down, there's still going to be an element of carbon dioxide produced. So you have to have that carbon capture. And if there's industrial scale carbon capture on the site, that's sensational, big win. And of course, that hydrogen, it's got to be somewhere where developers are looking to put hydrogen. So they tend to put their electrolysis plants and so on close to where process industry is. So you're probably looking at a former process industry site. That's what we've done. We've chosen a site in the northeast of the UK. We've not announced it yet. But it's on the site of a former British steel plant and ICI chemical processing factory. Those of you who've got any knowledge of kind of British processing history will be able to guess instantly from those two clues where it is. You've got to build the cost into your financial model. So you can imagine calling ourselves Green Lithium. A lot of people scrutinize what we do. They think, it's greenwashing. They're not really going to do this. So you've got to put yourself in a position where you're really going to do it. And you can only really do it if you can afford it. So when you build your financial model for the business case that supports the investment that's going to go into a project like this, you've got to make sure this is all costed out. You've got to make sure you've included for the extra expense of hydrogen, that you've included for the cost of carbon capture, that you've included for the electrification of the processes. All these things make it more expensive. So they don't come for free. If you're serious about it, you've got to build it in, and you've got to be able to demonstrate the affordability. So the financial model's got to stack up with all this increased expenditure in it. Something I come across a lot is a lot of industry partners who are delivering this kind of plant and project think you're just in it for the money. So when you say to them, have you looked at energy recycling on a plant like this? They say, oh yes, we did that for another project, but you start to kind of peel away and didn't understand what they did, and you realize they were just paying lip service to it. They don't really believe that this is important to you. So when you do these contracts with your delivery partners, you've got to make sure that part of their reward comes from reducing your carbon footprint. That way you can incentivize them, you get them in the right mindset of trying to reduce the carbon footprint. And when you get that right, you suddenly unlock this magical, cycle of let's get the carbon footprint down more. They start delivering to that ethos and they start trying to reduce the carbon footprint for you. So when you get that bit right and your delivery partners are aligned, then things really do start to work well. You can measure your progress with independent oversight. So that might be a separate committee on your board that looks at what you do. It might be a completely independent body that measures what you're doing. It might be through ongoing life cycle assessments to make sure you're reducing your footprint. But unless you've got that independent oversight, checking you, watching what you do, and that you set it up, then people won't take you seriously. And it keeps you on your toes. If you know you've got somebody looking over your shoulder, checking you're going to do something, you make sure you do it properly. So independent oversight is a really important part of the model. And then the final one really is about leadership. This is a change, it's a revolution. It's really exciting. I wasn't around for the first three revolutions, the coal, the oil. I was around for a bit of the gas, so I saw some of that happening. But it's a really exciting place to be. The whole world is changing. This huge industry that never existed before is sprouting out around us. And if you want it to go the right way, if you want it to evolve in the right way, you've got to set the standards for those around you. And that means you've got to walk the talk. So there's no point, talking 1 minute about reducing carbon footprint, but then missing an opportunity to do it, or whatever, failing to take opportunities when they present. You've really got to lead by example and be visible in encouraging green industry and sustainable ways of doing things. Only by doing that will we make everybody around us, all of the partners we work with, the customers we work with, the consumers who use those products, only by really raising awareness and walking the talk will we generate this very green, sustainable economy. And for me, that's probably one of the most important bits. It's surprising how many people don't really know how to get to green industry. And it's there, it's all technology that's up for grabs. A lot of it needs to be developed, it needs to be used, particularly with hydrogen. The only way we're going to get the cost of hydrogen down to economic levels is to go through that evolution of refining electrolysis and getting those processes working. So you've got to tell your supply chain partners, this is what we like. You've got to say to them, we'll buy hydrogen, we'll give you this much money every year. We're not expecting the price to come down, we just want more hydrogen for our money. So it gives them the constant throughput of money that they need to make their forward plans and try and make you more hydrogen. They've got a constant throughput of cash, so they know that they can rely on that. And then they just strive to give you more hydrogen for your money and meet your contractual demands that you've put on them. So the leadership is probably the most important one. And that is it. So, remember this, when you ever come to decarbonizing industry, it really is simple as whatever 7 letters are, A to G, I'm not sure. But at that point, throw it open to the floor. Has anybody got any questions? Yeah.
Thank you so much for your talk. I was wondering if you could tell us a bit more about the alkalization process.
So it really was just because, if you look at acid leach, you can map out the different various redox reactions that are used in hydromatology. And the temperature goes up, the pressure goes up. Alkali leach is one of the lowest, it's at the very bottom of the scale. And if you look at the curve of available technologies, it's right down there. So it was as simple as that for us. It was really the byproducts, knowing we had an inert byproduct, which if nothing else, we could just use it for construction film material. We knew it was inert enough. It could be used in some beneficial way, and trying to do it in a Western jurisdiction. So the alternative with acid leach is it produces sodium sulfate, and that's a chemical to watch in the future, because as more and more of these refineries, an awful lot of people are still going down the acid leach route. I think it's very unusual to go the alkali leach route. We've seen Piedmont in the US have adopted it. There's a company in Finland adopted it, and guess what? Tesla, love them or loathe them, but they're planning an alkali leach plant in America now. But just about all the other refineries are sticking with acid leach technology. So they still use the soda ash. They've got sulfuric acid leach. It means they produce hundreds and thousands of tons of sodium sulfate, which used to have plenty of markets. There were various reuse applications for sodium sulfate. But as that volume that gets produced goes up from the odd 100,000 tons to millions of tons, it's going to increasingly become a problem. And that just wasn't acceptable. Trying to get permission to do that in a Western jurisdiction would be almost impossible. They're finding it hard. There's 2 refineries in Western Australia that have adopted that technology, and they're already finding the permissioning difficult for the environmental permits, and it's just going to get harder and harder. To the point at which BASF, so BASF, the biggest cathode producer in Europe at the moment, sorry, second biggest after Umicore, they're now building a plant to reprocess sodium sulfate. So instead of letting it be a waste, they're actually going to invest even more money in turning the sodium sulfate into something that's reusable. So we've dodged all that by going the alkali leach route and finding this product that actually, without too much effort, you start to find some beneficial reuse of the material. That was a big thing for us. The energy reduction was the other. And then it's all around technical readiness. So how confident are you this process could work? It's never been built before. And with mineral processing plants, all the risk is in the scale up. So they've got it working at laboratory scale. They've got a pilot plant that happily chunks away. They've put probably 20 different sources of spodumene concentrate through it and produced really great yields, all in excess of 90%. But when you go from a plant that does, say, 1,000 tons per annum up to 25,000 tons per annum, as one of our lines do, that's a challenge. So we look really closely at the technical risks. What is it that stops the process from working? Mica's a problem. It interrupts with the hydromatology. We had to understand there was a way to get through that problem. Iron's a problem. If you put an iron-rich ore in one of these calcination plants, it forms a clinker. So instead of having a nice beta spodumene coming out, you get big clumpy lumps that you can't do anything with. So there's a lot of work that goes into the selection of the technology, but the big things for us were lower carbon footprint and reusable byproduct. Yeah.
Yeah, is there any thought being given to how you're going to recycle all the old batteries?
Get the lithium back? Great question. So the EU have come up with a battery directive, and this puts pressure, well, it demands that if you're making a battery in the EU that's going to be used in a vehicle in the EU, and the UK signed up to this, so there's no get out jail card there, then you've got to make sure it's recyclable. You've got to make sure that those materials can be re-extracted. And that's a change to where we are at the moment. Some of the batteries that were produced in the early electric vehicles, you couldn't even take the battery apart to get to the chemicals. So all you could do was shred it and produce a black mass material. Now, at the moment, there's not much, believe it or not, there's not much recycled material coming on the market, because the amount of lithium-ion battery in all the devices that we currently use, in all the power tools you use, in the current electric vehicles that are out there, is a tiny, tiny fraction of what will be out there when there's 20 million cars being produced in Europe every year, or with electric batteries in them. So at the moment, the recycling market's tiny, but it's going to be huge. So we're watching really closely to see what the emerging picture is with recycling. So most people don't understand that when you've got the black mass, all you've done is shred a battery. The real work is pyrometallurgy, hydromatology, solvent extraction to extract those different chemical elements. So we're watching really closely to see who works it out first, because the lithium that comes out of those batteries is going to be in some other form. Probably lithium sulfate, because when you're trying to convert black mass or getting black mass into a form where you can use solvent extraction, we're back to acid leach. unfortunately. So it's probably going to be lithium sulfate. So we're planning for a pre-treatment line that converts lithium sulfate back to lithium carbonate so we can reintroduce it into the main process and re-refine it for them to battery-grade chemicals. But, you know, to some extent, you've got to watch carefully before you commit, because it might be lithium sulfate doesn't dominate. It might end up being lithium carbonate or lithium phosphate. It just depends on the hydromatology processes that are selected by the people who are slowly getting into battery recycling. But the main forecasters say that by 2030, up to 40% of the material going into batteries is recycled, not from hard rock at all. So it's really important we look forward to that.
Can I continue that one? As I understand it, there is no worldwide shortage, particularly of lithium, but there is of cobalt. Yeah. And when you've got to recycle your batteries, you've got to get that cobalt back, otherwise the world will run out of cobalt.
Yeah.
Now, the next question following on that is, your heavy vehicles are going to use hydrogen fuel cells. Is it not easier to recycle and recover the materials from your hydrogen fuel cell, your precious metals, which Johnson and your experts have, and the smaller number of them? You know, your car might have 10 hydrogen fuel cells and it's got thousands of these tiny lithium cells. So maybe the heavy vehicle industry will get transferred down to cars and you'll be using hydrogen fuel cells, not the lithium-ion batteries, because of the problems of recycling. So
I'm very confident in I say that, you know, we need all of them. We need hydrogen, we need fuel cells, we need lithium-ion batteries, we're going to need sodium-ion batteries for some applications. This is all about electric vehicles. We haven't talked about grid storage or domestic storage, which are all going to all increase. And you know, if they all run flat out for the next 10 years, we've got some chance of delivering an electric revolution. So I think there's room for everything. What we are seeing, though, is a move away from cobalt-rich batteries. So the old NMC batteries are not old, but the NMC batteries are increasingly being replaced by higher nickel, higher manganese content, and of course the next generation of solid-state batteries, which don't necessarily need cobalt at all. You know, there are some designs which eliminate cobalt, but when I talk about recycling technologies, they are just as interested in getting the cobalt out as they are getting the lithium out. There's definitely some solutions out there now that can extract all the precious metals from recycled batteries. Just one point on the solid-state batteries. Again, there's no one solid-state battery, but predominantly they don't use lithium hydroxide at all. They're back to lithium carbonate. So old-style batteries, LFP batteries, they use lithium carbonate. The next generation is probably LFP. It's the bit in the middle that's hydroxide. So part of our refinery is to make sure we can equally produce battery-grade lithium carbonate for those future batteries. Otherwise, we'll run out of work in 10 years' time. Yeah.
Obviously, a lot of thought has gone through the decarbonisation of the mining process. Has any thought gone into the decarbonisation of the mining process? Obviously, it might not be happening in the UK, or the mining processes all around the world, as I said, sub-Saharan Africa. How is your company looking at decarbonising that process too?
Yeah, another great question. So when you do your carbon life cycle assessment, you look at the whole life cycle. So you don't just look at the process you're doing, you look at the upstream and downstream elements as well. And we worked out that actually the mining side is a significant contributor to our carbon footprint. So if we continue to source material from Western Australia, about 6 kilograms of CO2 per kilogram of lithium hydroxide comes from the mine. About a kilo of that is shipping it from Australia to the UK. So a very obvious thing we can do is stop shipping it from Australia and just ship it from mines closer to home. And that's why Africa works really well. So particularly Namibia and Mali and Ghana, because they're all on the west coast, smaller shipping leg. But we're increasingly trying to work with mines who are trying to achieve carbonate zero. And it's not just the mines, it's also the lime producers. So most of the lime is produced in the UK, pretty much all of it comes from Derbyshire. It's got a really high carbon footprint. They use calcination processes exactly the same as us, except they learn, you know, because they're typically cement companies, that they're quite backward in terms of the processes they use. They'll burn anything. They'll burn oil, they'll burn waste, flammable chemicals. They're not quite in the place where they're thinking of using hydrogen because they just can't make a business case for it. But increasingly, if you choose the right ones, they are. They're talking about linking up with the Northwest cluster of carbon capture and using hydrogen. So you choose your partners carefully to make sure they've got a roadmap to reduce their carbon footprint. Australia's got work to do. You know, their energy mix is quite carbon intensive. Ironically, places like Namibia, where they're talking about using a lot of solar power to make hydrogen, could be a great place to work with, because the carbon intensity of their production, of their energy needs, is much, much lower. So you choose your partners very carefully, and then you get the benefit of their carbon reduction plans as well.
Another question about the byproduct. And I appreciate that you said earlier on very clear that you can't say too much about things. If something is to be made sustainable, to use that term is self-used at the moment, then that should really mean not just next 10 years, 20 years, but indefinite, in principle. Okay? So if the perceived market for the byproduct is currently the cement industry, and if, as a result of everything scaling up, there's a glut of that, have you identified, or has the company identified, other sources of possible use for it?
Yeah.
Other markets for it?
Yeah, I mean, so the first thing to just mention is Green Lithium is a very small company at the moment. There's 10 people in the whole company. So have we got a complete answer to that question? No, we haven't yet. But over the summer, we had an intern student just concentrating entirely on reuse markets. We'd come up with about 20 different potential markets for the material, which were frankly just, you know, harebrained schemes, a lot of them. So we went through each one of them systematically to identify if it's real. You know, for example, they use something similar to an alcine in glass fiber production. And you know, 19 other potential uses, everything from ground improvement to, as I said, filling in Croft Quarry, which was an old granite mine with lots of an alcine in it. So there's lots of reuse potentials. It simply won't be down to one market. It can't be down to one market. We know the coarse fraction of the material can just be a straight aggregate in ready-mix concrete to be used in concrete block manufacture or something like that. And it's the only way we'll achieve true sustainability is by diversity of markets. So it's really important we work on that and build any post-conditioning into the design of the plant now, rather than wait until it's too late.
Thank you.
No, have you heard about this prospect of reopening a Cornish tin mine to produce lithium? And one of the things I think they said was they were talking about recycling or trying to recover the lithium from the spoil from tin mining.
Yeah.
Now, I always remember chemistry in here that all sodium salts are soluble, most of the potassium ones are. I'm quite sure about lithium, but if you've got a spoil heap of lithium in it, would that not leach out with the water that's raining on it?
You just passed my knowledge threshold. What I would say is I know that so Imerys were sort of China clay mines. Some of their tailing arisings did still have some lithium in. I think before Green Lithium looked at refining, we did look at that. We were looking at UK sources of lithium to see if we could find something locally. They did some sampling from some of those spoil heaps. They also took samples from other geographically high potential areas to see if there was anything that could be used on a commercial basis. And when you compare it to something like 5 or 6% spodumene concentrate, which has got a lot of lithium in it, nothing seems to stack up. So having said all that, I think some of those plans, particularly the direct lithium extraction technology they're proposing for geothermal waters down in Cornwall, could be interesting because it's very low carbon, it's very sustainable. But again, there's questions over how replenishable those supplies are. So once you take one round of lithium out, how quickly does it regenerate and pick up more lithium from the bedrock? So we moved away from that. We thought that didn't look promising enough to sustain the business model.
We've got a question here
Yeah.
from the chat asking if the product transported is in special packaging material.
So the product, yes, absolutely. But it only has to be sealed. So it's classically put in plastic bags. and then in 200-litre drums just to prevent any air or moisture getting to it. But that does put up the kind of shipping costs a little bit because you know, you're containerizing it rather than bulk transporting it. But yeah, absolutely, you've got to make sure it's airtight. Probably more importantly is how you package it. If you look at battery technology, they hate iron. They hate remnants of iron because if you put iron in a cell, you know, classically it's a good conductor and doesn't really work very well. So levels of iron contamination in cathodes tend to be incredibly low. And we've got some feedback from the industry around you've got to be really careful with processing and packaging, because if you're grinding it, crushing it, or preparing it as a powder, a lot of these processes can, you know, leave an iron residue in the material, not from the original source material. This is your process can introduce iron, and that can cause a real problem. So it's an area you have to give a lot of emphasis to, otherwise you could find yourself making non-compliant material. Any questions? I think I've got away with that.
Yeah. Thank you for that.
Thank you very much.
So thank you for the talk, Sean. Yeah, so there will be like post-talk activities back in the Whitehall room. So yeah, thanks again, Sean. And just to remind everyone, this talk was sponsored by the FBI, and we've got members here tonight. So if you are interested, please do take this chance to talk to them. Perfect.
Thank you.